So I'd like to talk about Rutherford scattering next. Remember, in order to get an introduction to the nomenclature of scattering, watch the hard sphere scattering lecture first. But I'm going to jump right in now to Rutherford scattering, assuming that you're familiar with the nomenclature and the ideas from hard sphere scattering. So you sort of have to place yourself in the historical context to understand the Rutherford scattering experiment and make sure that you understand all the implications. And so people at the time were trying to figure out what the atom was really like. Now, J.J. Thomson, who was the person credited with the discovery of electron and measured the charge to mass ratio of the electron, based upon his work, he developed a model of what he thought the atom was like. So they knew that atoms were neutrally charged, and that therefore they had to have both positive and negative charges within the atom. And since they knew that electrons were point-like particles, what they envisioned originally as the atom was sort of more like Thomson's model. And Thomson's model is called the plum pudding model of the atom. He pictured the atom as sort of a spherical dough, positive dough, with these little embedded electrons in it, very similar to a plum pudding where you have a bread dough with little raisins scattered throughout it. Okay? And so that was one conception of the atom. Now, in order to test this conception of the atom and maybe figure out what atoms were really like, Rutherford carried out a series of experiments in his lab, and Geiger and Marsden actually conducted the experiments, and then Rutherford modeled their results. So these experiments were conducted between 1909 and 1913. So the setup for these experiments was they took a source of alpha particles. Alpha particles are just helium nuclei, right? So 2 protons and 2 neutrons. And then they accelerated the alpha particles away from the source, which was a radioactive source. So they accelerated these particles away from the source by using a voltage, and they collimated the beam by a series of pinholes. And then they had these highly energetic alpha particles incident on a very thin gold foil target. I believe the thickness was about 600 nanometers. And then they had detectors set up in array around the gold foil, and they measured the angle at which the alpha particles were scattered from the thin foil target. Now, what they found was actually really surprising. I'm going to quote Rutherford here. He said, "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. On consideration, I realized that this scattering backward must be the result of a single collision, and when I made calculations, I saw that it was impossible to get anything of that order of magnitude unless you took a system in which the greater part of the mass of the atom was concentrated in a minute nucleus, and it was then that I had the idea of an atom with a minute massive center carrying a charge." So what he's referring to here is the fact that these particles, these alpha particles, were scattered at all, much less that a small fraction of them were scattered almost completely straight backward. See, if you think of it from the idea of Thomson's idea, the model of a nucleus, the alpha particles were much larger, right? They had a much larger mass than these tiny little electrons. And so the idea that something so massive could be scattered off something so tiny was just crazy, like a 15-inch shell being bounced off a piece of tissue paper. So instead of this, Rutherford developed a model of the nucleus where almost all of the mass of the atom was concentrated within this very, very tiny nucleus, this very, very tiny nuclear charge. And all of the positive charge of the atom was concentrated within the nucleus, and it scattered off that dense center core. So that was his idea, all right? So now I'm going to talk about the equations that Rutherford used to model this. I'm not going to go through the derivation. I feel like that's a little thick for an online lecture, but I'll present the results and then we'll work some example problems with those results. So I think it's important, though, even if we don't go through the derivation, that you understand the assumptions that Rutherford made when developing his model. Now, in a previous lecture, we talked about hard sphere scattering. Now, that's really basic, and Rutherford scattering is a little bit harder than that. In hard sphere scattering, your incident particle and your target actually bounce off of one another. They actually physically contact, and that's a little bit easier to conceptualize. What's happening in Rutherford scattering is that the nucleus and the target, or the incident particle, don't actually touch one another. Instead, it's a repulsive Coulomb force that causes that scattering, that F is equal to 1 over 4 pi epsilon naught Q1 Q2 over R squared force, right? It's a very strong force, and it repels the incident from the target before they can touch. Now, another assumption that he made is that the scatterer is so massive that it doesn't significantly recoil, and so the initial and the final kinetic energies of that alpha particle are practically equal. We're going to assume that the target is really thin, so that pretty much only a single scattering event occurs, and we're going to assume that the bombarding particle and the target scatterer are so small that you can treat them like point masses and charges. All right, so here's kind of a picture of what the scattering event might look like. Now we're still going to talk about the impact parameter B. Remember, the impact parameter is that center-to-center offset distance between your incident particle and your target. So that if you drew a straight line for the incident path of your projectiles, and then how far offset that is from a parallel axis that runs through the center of your target. So that's the impact parameter. And it measures the effective nuclear size. And remember that the scattering cross-section is going to be pi b squared, because you're looking sort of at a photo, a snapshot, and seeing how far away from the center of that nucleus you are, and calling that the effective area of your target. Okay? And we're calling it an effective area of our target rather than a true, because we're treating them as point particles, basically. Okay, so the impact parameter B in this case is equal to the product of the charges of the incident particles, the alpha particles, and the target nucleus, that charge. So that's going to be Z1 times E times Z2 times E, where Z1 and Z2 are the atomic numbers, respectively, of your incident and your target, and E is the fundamental charge. Now you're going to divide that product through the charges by 8 pi epsilon naught divided by the kinetic energy of your incident particle, and then times the cotangent of the scattering angle over 2. All right, so that's the angle, or that's the equation there. Now K here is the kinetic energy. What you're going to do is assume that when you're infinitely far away, you've got all kinetic energy, and the accelerating voltage times the charge there will give you the kinetic energy of your particle. Okay? So that's your impact parameter B. Now, just like in hard sphere scattering, the probability of that particle being scattered, shown here as a fraction f, is equal to the total target area exposed for all nuclei divided by the total target area. Okay? Contact isn't necessary for the scattering. Okay? So that's going to be NT A sigma divided by A. Now N here is the number density of nuclei per unit volume. So here you have the number of nuclei per unit volume in your target, that's N. And T is the thickness of your target. For the gold foil, that would be 600 nanometers. And then sigma is that scattering cross-section, which is pi b squared. So the fraction of particles scattered at an angle greater than theta is nt pi b squared, where b is your impact parameter, z1 z2 e squared over 8 pi epsilon naught k times the cotangent of theta over 2. All right? So that's the fraction of particles scattered at an angle greater than theta. Now, if you want the probability per unit area for scattering into a detector, remember your detectors have a finite area, okay? And it's easier sometimes to measure an intensity or a scattering rate than it is to measure the total number of particles, right? Because you're measuring a number per unit time. That gives you an intensity. So if you do that, then what you do is you take the derivative of that fraction that we presented earlier with respect to A, and then you can derive the Rutherford scattering formula. And that Rutherford scattering formula presented here is n of theta is equal to nt over 16, e squared over 4 pi epsilon naught squared, z1 squared z2 squared divided by r squared k squared sine to the fourth theta over 2. Okay? Now here, yet again, theta is that scattering angle, and r is going to give you the distance from your target to your detector. Okay? Now, this experimental equation that he derived precisely fit the data. Okay? And so, since he had such good agreement with Geiger and Marsden in his experimental results, Rutherford and his team are credited with the discovery of that nucleus. So it's a pretty amazing accomplishment. Now, you can often see a lot of different problems associated with Rutherford scattering in introductory physics classes. And one of the most common questions they like to ask is, what's the distance of closest approach, which could give you the effective size of a nucleus? And this was also a calculation that Rutherford carried out, by the way. And so, in that case, you would have the effective nuclear size. It would give you the best approximation if you did a head-on collision where B was equal to 0. And then what would happen is you would have the closest possible approach, and we're going to call the distance of closest approach D, of the particle to that nucleus. And so you can think of it this way. If you assume that infinitely far away from your target, your scatterer had pretty much your incident particle had all kinetic energy, and then as it approaches the nucleus, it's got to turn around and go back the other way. And when it turns around and goes back the other way, for a split second, it's come to a stop. And what that means is that all its initial kinetic energy has been converted into potential energy, that Coulomb potential energy between your incident and your target nuclei. And that's going to equal to the Coulomb constant, 8.99 times 10 to the 9th, times the product of the charges of those two nuclei, little q and big Q, divided by the distance of closest approach, d. So if you set that equal to your kinetic energy, then you can solve for that distance of closest approach. And that distance of closest approach would be your Coulomb constant times the product of the two charges divided by the kinetic energy, and then you could solve for that. So I've done that here for Rutherford's experiment, all right? He had an alpha particle and he had a gold nucleus, and the charges on those are 2e and 79e respectively, plugged in for that, plugged in for my Coulomb constant. The initial kinetic energy of the alpha particles was 8 mega electron volts, and then I converted that over to joules, and I solved. And the distance of closest approach that you get is 2.8 times 10 to the minus 14 meters. So this was the effective nuclear size for this experiment. Now bear in mind that an atom is on the order of 10 to the minus 10 meters. You can figure that out by doing some density calculations. It's really pretty simple to do that calculation. And so Rutherford knew that he was looking at something, an effective approach, that was teeny compared to the size of the atom, at least 4 orders of magnitude smaller. All right? So that's how he came up with his idea of a minute massive center that had a densely packed charge in there for the structure of an atom. Now you can also work problems where you calculate the fraction of particles scattered using that formula, F is equal to nt pi b squared. So let me do an example of that. For an 8 MeV alpha particle incident on a gold target that's 600 nanometers thick, what fraction of the particles would you expect to be scattered more than 1 degree by a single scattering event? So if I plug in for all those things, nt pi b squared, I've got to first calculate b. And so this is going to look really similar to my previous calculation for the distance of closest approach, except instead of dividing by just 8 MeV, I've got to take half of that. So I have 8.99 times 10 to the 9th, that's my Coulomb constant, 1 over 4 pi epsilon naught, times the product of the two charges, 2e and 79e, divided by 2, divided by the kinetic energy of the incident particle, 8 mega electron volts, converted over to joules, and then the cotangent is just 1 over the tangent, and half the angle would be 0.5 degrees. So if I plug all that in, then I get B is equal to 1.6 times 10 to the minus 12 meters. Now, I need a few other things too. I need to know the number density of the nuclei, right? So if I use the density of gold, which is 19.3 grams per centimeters cubed, and I convert from cubic centimeters to cubic meters, and then use the atomic weight of gold, 197 grams per mole, and then also Avogadro's number, 6.022 times 10 to the 23rd, then I can get the number density of nuclei. And that gives me 5.9 times 10 to the 28th inverse cubic meters. Now, if I multiply that times my thickness of the foil, sorry here, I've just got a little mistake there. So if I multiply 5.9 times 10 to the 28th times inverse cubic meters times the thickness T, which for the Rutherford gold foil experiment was 600 nanometers, times pi, times what I found for B, 1.6 times 10 to the minus 12 meters, and then square it, then I end up with 0.29 for my fraction, which would mean that 29% of my particles would be scattered at an angle greater than 1 degree. All right? Now note that this doesn't take into account the finite area of the detector and over exactly what angle. It just shows how many would be scattered at 1 degree or more. And given that, 29% really isn't very much. Okay, so continuing on, Rutherford developed a model of the atom based on his idea of this dense nuclear charge in the center. And he hypothesized that the electrons would orbit that nucleus like the planets do to the sun because of the Coulomb attraction in between the positively charged nucleus and the negative electrons. Okay? And this was as a result of his thin foil experiments. But right away, he and everybody else knew that there was a problem with this idea. And that's because accelerating charges radiate energy. And so the problem would be that your electron is traveling in a circle, and hence there's got to be a centripetal acceleration, right? That means your particle's accelerating, and it's going to radiate that energy. And as it does that, it would lose energy until eventually it would spiral into the nucleus and just fall and hit and crash in. So everybody knew that this model wasn't stable, okay? However, it took some advancements and thought experiments by Bohr to come up with a slightly better model. And then of course now we understand that even Bohr's model has flaws, and that quantum mechanics and the solution to the Schrödinger equation gives us the true picture of the atom. Okay, but for now, we'll stop there. I hope you enjoyed it, and I'll see you next time.